Now that we have constructed Hilbert spaces and orthonormal bases, we can see some of their distinguishing features. One of them is norm conservation, which is called Parseval's theorem and is an extension of Pythagoras' famous orthogonality theorem to infinite dimensions. Then we will see the orthogonal projection theorem. This is a powerful method to take a vector from possibly an infinite dimensional space and project it onto a subspace. Once we have this, we will consider some examples of approximations and orthonormal bases. Module 3.3, Hilbert space and approximations. The overview of this submodule is the following. First, we're going to talk about the norm conservation when we have expansion into orthonormal bases and a so-called equivalence formula, which is known as Parseval's formula. Then we talk about approximation by projection, and we give an example. Parseval's theorem has a very simple form. It says that if you expand x in an orthonormal basis, so we have a vector in a Hilbert space, we expand it in an orthonormal basis with this vector w. Here we are in a finite dimensional case of dimension capital K. Then, for an orthonormal basis, the square norm of x is equal to the sum of squared coefficients. Okay? This is, of course, a generalization of Pythagorean theorem, which says that if I have a vector here, this is x, this is the length in an orthonormal basis, so that would be alpha 0 in E0, alpha 1 with respect to E1, then x square is equal to alpha 0 square plus alpha 1 square. Okay? Very old result, very useful result. Let's actually verify it algebraically. We start with a canonical basis, E0 and E1, just as before. We write x as a linear combination of E0 and E1. And we go to a new basis. The new basis is V0 and V1. It's an orthonormal basis. Okay, you can verify that these guys are at the right angle. And this basis is given by V0 is cosine theta sine theta, V1 is minus sine theta cosine theta. You can see this here on the projections. And so x in the new basis is equal to beta 0 V0, beta 1 V1. What are the expressions of this? Well, we know this because the basis is orthonormal. So the expansion coefficients beta 0 is equal to the inner product between V0 and x, beta 1, the inner product between V1 and x. Or in compact form, we can just write these inner products as row column scalar products. Okay, so the V0 is cosine theta sine theta, V1 is minus sine theta cos theta, as we have seen. And so we write this as R times alpha, where R is a rotation matrix. Okay? It's a unitary matrix that corresponds to these basis vectors. All right? And it's not hard to verify that the rotation matrix times this transpose is equal to identity, meaning it is equal through transposition to its inverse. So it's a unitary matrix, as we probably well know by now. Okay, so let's look at norm conservation. So the square norm in the canonical basis is just as we announced, so x squared is equal to alpha 0 squared plus alpha 1 squared. The square norm in the rotated base is the same, but with respect to beta. Okay, so we are going to show that these two things are the same, or verify Parseval's formula. Well, one way to write beta 0 squared plus beta 1 squared is to say it's a vector beta transpose times beta, right? Okay, so I'm making myself absolutely clear. It's a scalar product of the vector beta, okay, with itself. Okay, that's the thing here. Now, of course, beta is equal to R times alpha. Beta transpose is R times alpha transpose. You go to the extra step of reordering here the product, so the alpha transpose comes in front, R transpose here times R times alpha. This, of course, simplified to identity, that we know, because R is a unitary matrix, so this is equal to alpha transpose times alpha. And, of course, we verify what we set out to do. Okay, now we did this in 2 dimensions. It's obvious that this will hold in n dimensions for an arbitrary n. It turns out it also holds for infinite dimensional orthonormal bases. Okay, so that's Parseval's formula, very important formula in signal processing. Okay, what it really means is that if you have a vector x and you look at this vector in this basis, and you look at it in some other basis, as we just did, which is a rotation, because all unitary bases are essentially rotations of each other and maybe some symmetry, then the length of the vector doesn't change. Okay, so that's, of course, norm conservation also means distance conservation through these transforms or through the expansion into orthonormal bases. All right, the next step we want to do is approximation. We had briefly mentioned this at the beginning of this module. So you have a vector in R3 here, and the vector x should be represented in a subspace spanned by E0 and E1. Well, that's a subspace S of V, spanned by E0, E1, now shown in red. And the approximation is x hat, which belongs to S, and it's the orthogonal projection x to the plane spanned by E0 and E1. Okay, and that orthogonal projection will denote by x hat. How can we do this? It is very simple. We take an orthogonal basis for the subspace. Okay, so remember we have the big space V, we have the subspace S. So we take an orthogonal basis for the subspace, and the orthogonal projection is simply going to be given by x hat expanded in the orthogonal basis that spans the subspace. Okay, so the set of vectors Sk is the orthogonal basis for S, and here is the expansion formula in this orthonormal basis. This orthogonal projection is the best approximation over S to the vector x, and it's best in the L2 sense, or it will minimize the quadratic norm of the error. Okay, so said in word, orthogonal projection has minimum norm error, so among all vectors y that belong to S, the one that minimizes the square of the difference here, so the square norm of the difference x minus y, is this vector x hat that we have written out in terms of an orthogonal basis for the subspace S. Very important property is that the error x minus x hat is orthogonal to the approximation. Okay, so we'll see it in the next slide, but this is an extremely important formula. It's called the orthogonality principle. It is used all over signal processing when we minimize quadratic error. All right, so let's see this very graphically. We have S, a subspace. This guy is subspace of V. V is the ambient space here. In this particular case, R2. S is R1. It's a one-dimensional subspace. Okay, so we want to find the closest point to x. So x is what we want to approximate. We'd like to find the closest point somewhere here on S. Okay, how do we do this? It has to be closest in the 2 norm. So we create a circle around the tip here of x, and we grow the circle. Okay, we are still not at S, and at some point we reach S. This is clearly the closest one, right? Because the circles measure quadratic distance, and the first time we hit S is exactly here. Okay, so we have x hat in blue, and we notice that x minus x hat, the red vector, is orthogonal to the blue vector. That's the orthogonality principle we have seen on the previous slide. Let's look at a very concrete example. It's polynomial approximation. So we go back to our favorite interval -1 to 1. Okay, so we look at these guys, and for this interval we define a subspace Pn -1 to 1, which are polynomials up to degree n minus 1 on the interval -1 to 1. Okay, so a basis for this is simply to take as the successive monomials tk for k going from 0 to capital N minus 1. Okay, so a naive basis here is really 1 t, t square, t cube, etc. Okay, now these guys are not orthogonal to each other. Okay, this naive basis is not orthogonal, okay, which is self-evident because, for example, on the interval minus 1 to 1, let's take this interval, we have the first element is this guy, okay? The second guy is orthogonal because the first one was symmetric, the second one is antisymmetric, but the third guy is a quadratic function, and it's not properly scaled, I apologize, but the quadratic function, of course, is also symmetric. So, for example, the inner product between 1 and t square on the interval minus 1 to 1 is not equal to 0. Okay? Please check this more explicitly if you like, but it's fairly geometrically evident. Okay, now we're going to try to approximate something that does not live on the polynomial space. So that would be, for example, a trigonometric function. So take x, what we want to approximate as sine t over minus the interval minus 1 to 1. And we would like to approximate it on P3, so up to polynomials of third degree. Okay, so the way to do it is we build an orthogonal basis from the naive basis, we project x over the orthogonal basis, we compute the approximation error. Okay, so same thing as usual. So S here is this P3 space. Our sign is somewhere out there, and we want to compute this. To do this, we first construct an orthogonal basis for the subspace S. Okay, we can compare this to the naive approximation, which would be Taylor approximation. It's well known, very useful, but it's not optimal, as we will see in just a minute. Okay, so from the naive basis, remember we have the naive basis, it's 1 t, t square, t cube, etc. We can compute, so that's a biorthogonal basis, we compute an orthogonal basis. There is a procedure to do this, which is called the Gram-Schmidt algorithm. Okay, it is explained in the appendix of this lecture. We are not going to do it in the main lecture. And it's a recursive procedure where you take the first one, you normalize it, that's fine. You take the second one and you make sure it's orthogonal to the first one, you normalize it, and you keep going. And the result of this is that you get orthonormal vectors, u0, which is just a scaled version of 1. The second one, these two are orthogonal, so you don't have to change much except for the scaling. The third one is a transformation of t square, let me make this more explicit, t square, into, a second order polynomial, which is constructed such that u2 is orthogonal to u0 and u1. And you can keep going like this. It's a standard construction, it's called Legendre polynomials, and just from the name, you know this is a 19th century construction, so it's extremely well known, and the appendix gives the details. Okay, so now we have an orthogonal basis for the subspace. And let's just watch these Legendre polynomials. They are sort of cute. So the first one, remember, it's 1 over square root of 2. So here we go. That's 0.7 something. It's a black line. The second one is proportional to t, but it has been scaled. The third one, which is quadratic, has been moved about. So now it is actually orthogonal to the yellow curve is automatically orthogonal to the red curve because one is symmetric, the other one is antisymmetric. But the shift that was added, if we go back here, let me just show it, there's a shift here. This shift makes sure that the inner product between the yellow curve and the black curve is 0. Okay? And the fourth is a third degree polynomial, the green guy. It is antisymmetric, so it will be automatically orthogonal to the black one, the yellow one, but it has to be adjusted so that it's also orthogonal to the red one, and we can keep going. Okay, that's a fourth order guy. fourth order polynomial, and so on. So Legendre polynomials go off to infinity, but we just look at a few of them. Okay? Here's a fifth one, and it's a very cute picture. And this set of polynomials on this interval -1 to 1, okay, very important, on this interval, it's defined in such, it's constructed actually in such a way that the inner product of two of these functions is equal to delta I minus j, so it's equal to 0 when I is different from j, and it's equal to 1 when I is equal to j. Okay, it's not self-evident when you look at the functions, except for the symmetries that I pointed out a minute ago. All right, so now we can compute our expansion coefficients. Remember, we want to write a formula where x hat is going to be some sum of alpha k uk, we call these guys here, and you know, k goes from 0 to capital K minus 1, so that's the orthogonal projection onto the subspace spanned by the uk. All right, so we have to take the integrals between -1 and 1 of the functions, these polynomials we have just defined, Legendre polynomials, and the function we want to approximate, sine t. Okay, so sine is of course an odd function, as we know, and so alpha 0 is going to be automatically equal to 0. Alpha 1 is going to be different from 0 because both u1 and sine are odd functions, so that's what you get if you do the integral, 0.73 something. And the third coefficient, alpha 2, is also equal to 0 because this character here is symmetric and this one is antisymmetric, so it's automatically equal to 0. Okay, so what do we get? So when we do the orthogonal projection on these three basis vectors, so u0, u1, u2, we get an approximation which is simply alpha 1 u1, and it's given by this formula. If we do Taylor series, then the first order approximation of Taylor series is simply to take sine t equal to t. Okay? And so we're going to compare these two approximations. They look very similar, but one has been scaled a little bit. Okay? All right. So now we see that the approximation of sine, which is a blue curve, the smooth blue curve here, t is the red curve, and green is simply a scaled version. Doesn't look like a big deal. It's 10% smaller, but you can immediately see that it's actually hugging the blue curve more closely over the interval -1 to 1, right? So we are approximating this over this interval. If we change the interval, the approximation would look different. Okay? But over this interval, as we can see here, we plot the absolute value of the difference. The red one is sine t minus t. Okay, it goes off quite a bit at the end intervals here. It's very nice in the region around the origin. Okay? And we see that the green approximation, which is sine t minus our projection onto the subspace of the Legendre polynomials of order 0, 1, and 2, that error is overall it is smaller. It never goes off to these values. Okay, sometimes it's bigger, but overall it actually turns out to be smaller. Okay, so to compare this numerically, we can compute the norm of sine t minus alpha 1t, and it's 0.03. In Taylor series, it's almost 3 times bigger. It's 0.08. Necessarily, we have to be as good or better than Taylor series because it's a theorem. It's the orthogonal projection theorem. We find the minimum norm approximation. Okay, and with this, we have shown on a very practical example how to do orthogonal approximation using an orthogonal basis. Now, this was all a lot of work. We defined Hilbert spaces, we had a lot of definitions and so on. So why do we do all this? It's a valid question. So first is that both finite lengths and periodic signals live in Cn, so we can use all of linear algebra and all the geometry of linear algebra to do this. And infinite length signals that we like for general signal processing live in a more general Hilbert space, which is small L2 of Z. Okay, so we have a common geometric framework for both finite length periodic signals and infinite length sequences. Okay, so we have one way to think about a whole bunch of different problems. Okay, then we'll see that the expansion into orthonormal basis is very central to signal processing. So we can use different bases as different observation tools for signals. We're going to see something called the short time Fourier transform, to be defined in module 4. And the short time Fourier transform, as the second half says, is something like a Fourier transform, but it's a very particular way to look at signals. It's very popular for doing speech analysis and the like. Okay, and when we do subspace projections, we will see that we can do filtering, which will be explained, of course, in detail in this class, and we can do, for example, image compression. Okay, so the notions we have seen, one was to build bases. That's important. These are like our tools to look at signals, okay? And another one was subspace projection, which was something that will come a lot when we do approximation and in particular when we do compression. Okay, let me just finish this properly here. We have an origin, we have a subspace S, we have X, and we have an orthogonal projection, and we have the orthogonality principle.